This video is for lesson 8-7, applications of inverse variation. So this is the same section as yesterday. We're going to do some word problems. A surface is 10 feet from a source of light. How far from the source would the surface have to be to receive twice as much illumination if the intensity of light varies inversely with the square of its distance from the light source? So this problem involves intensity of illumination. Let's use the letter I to represent that. And it involves the square of the distance, maybe the letter D for distance. So in this very last part of the sentence, we can get our relationship. The intensity times distance squared is equal to a constant. This question is interesting because when we recently built our house, the electricians came in to discuss where to put the lights. And they had to do this kind of algebra to know how many of the lights to put to have the room be bright enough for whatever the purpose of the room was. Now that we have the general model that relates intensity of light and distance, we can use the first sentence to figure out what K is. It says the surface is 10 feet from the source of light. That's a distance. So for the letter D, you can fill in 10. We now need a value to fill in for I. But nowhere in the problem does it give us a specific amount of illumination. But what is mentioned is we want to know about when there's twice as much illumination. So it doesn't matter what number we use for I. We're just going to pick something, and then later we'll use a number that is twice as much. So for I, I'm going to choose 1 because that's a really easy number to do math with. And that is equal to K. Solving this out, we get 100 is equal to K. Then rewrite the model and fill in K. The question asks, how far, so that's a distance, would the surface have to be to receive twice as much illumination? So in place of the letter I, because I used a 1 last time, I'm going to fill in a 2. That would represent twice as much illumination as the first situation. The letter D is our variable, and that's equal to 100. Now we want to solve this equation for D. So divide by 2 on both sides. D squared is equal to 50. Then, how do you remove squaring? With square root. So D is equal to the square root of 50. We could simplify this by breaking it up into 25 times 2, and that equals 5 square root of 2. Or because this is a real-life problem, getting a decimal would be a good way to answer this question. Take the calculator and type in the square root of 50, and you find out that the result is 7.1. This distance is measured in feet. So this situation is something that an electrician or an expert in lighting would know about. To receive double the amount of illumination from a light, you'd have to move it about 3 feet closer. It was 10 feet away, but if you move it so it's only 7.1 feet away, now twice as much light will reach to the surface. Here's our next example. The amount of bending of a beam supported at each end and centrally loaded varies jointly as the load and the cube of the length. And it varies inversely as the cube of the depth. So this is an engineering question about how strong a metal beam is. So on the side here, here's a metal beam, and it says it's loaded centrally. So it's carrying a weight from the center. Either that weight is hanging down underneath, or maybe it's just loaded up with a whole bunch of heavy stuff right here. That weight is going to cause the beam to flex. It's going to bend a little bit in the middle. And as long as it doesn't bend too much, then that would be okay to construct something with that beam. From this first paragraph, we're able to create relationships between amount of bending. Let's choose a variable for that. Maybe B for bending. And the load, that's in pounds, maybe the letter L to mean load. And the length, we already used L for load, so we did another letter for length. I'm going to use S. And then later on I read depth. So we need a letter to be depth. Maybe the letter D. Let's read this again and create the model from that. It says that the amount of bending varies with the load and the cube of the length. So bending is equal to some constant times the load times the length cubed. And inversely as the cube of the depth. So we divide this by depth cubed. This model comes from this first paragraph. Now in the next paragraph, we have numbers that we can fill in. So it says the beam is 12 feet long. So the letter S was representing length. I'm going to fill in a 12. It says it's 6 inches thick. So that's the depth. So where the letter D was, I'm going to fill in 6. Then it says it's carrying a load of 2,000 pounds. That was the letter L. So where L is, fill in 2,000. And it says it bends 1/4 inch downwards. That was the capital B, 1/4. Remember that our model also had the letter K in it, representing some constant that we have to figure out. So we have 1/4 equals K times, and then I filled in the other numbers. Now let's solve this for K. So in the first step, take a calculator and type this entire piece in right here to get it as a single number. We'll have 1/4 equals K times 16,000. Then we can divide both sides by 16,000 to get K alone. 1/4 divided by 16,000. This makes 0.000015625. Now rewrite the original model, but this time fill in that value for K. Finally, we're ready to go to the last paragraph where it asked us, what is the maximum load? That's the letter L. So we want to find an answer for L when we're able to fill in every other letter with a number. So it says we have a 16-foot beam. That's the length, which I was using the letter S for that. So here is the value of K times L, and then where S is, fill in 16. That's divided by D cubed. Well, D was representing depth, and it says the depth is 4 inches. So fill in 4 for D. And we don't want it to bend more than 1 1/8 inches, and that was capital B. So fill in 1 1/8. Here is an equation where all variables are filled in except for the load. So if we solve this for L, we will have found the maximum load. Take a calculator and do all the work on the right side that's next to the L. Take this number times 16 cubed, divide by 4 cubed. It turns out to be 0.001. So we have 1 1/8 is equal to 0.001 times L. Now what do you do to get L alone? Divide both sides by 0.001. We will get L equals 1,125. What unit of measure was load in this problem? It says up here in the first paragraph it's in pounds. So if a beam is 16 feet long and 4 inches wide, and we don't want it to bend more than 1 1/8 inches, the maximum weight you can put in the center is 1,125 pounds. This problem shows the kind of algebra that an engineer would use.